let us take up a few failures of this octet rule. Octet rule says that for a molecule to remain stable, all the atoms of the molecule should have their octets or duplets completed. Only then the molecule may remain stable, otherwise not. However, there were quite a few stable molecules found wherein the central atom did not have its octet completed and still the molecules were stable. For example, something like BeCl2. The central atom beryllium has only 4 electrons around it, doesn't have its octet completed. Something like Bf3. The central atom boron has only got 6 electrons around it. Its octet is not completed. Something like AlCl3. Aluminium has 6 electrons around it, and the octet is still not completed. So here, beryllium has 4, boron has 6, and aluminium has 6 electrons around it. Their octets are not completed, and still these molecules remain stable. As per octet rule, these molecules should not remain stable. So all these the stability and existence of all these molecules defy the octet rule. Second, we also have molecules like PF5 or SF6 which are stable. Now if you consider something like PF5, the central atom is phosphorus and would have about 5 fluorine atoms around the phosphorus. So you have phosphorus with 5 fluorine atoms around it. That would make a total of 10 electrons around phosphorus. Or for something like SF6, right, sulfur would have about 12 electrons around it. So here, the central atom has more than 8 electrons around it. Such octets are called expanded octets. So we say there are molecules, there are stable molecules like PF5 or SF6 with expanded octets around the central atoms. So this also is not as per the octet rule, right? Octet rule says that an element should have only 8 or at times 2 electrons around it, and otherwise it may not remain stable, right? So we have molecules where central atom has less number of electrons, less than 8 electrons around the central atom, and still remaining stable. And we have molecules wherein the central atom has more than 8 electrons around the central atom and still remaining stable. The third failure is very surprising. Recently we found some molecules like XCF2 or XCF4 or even XCF6. Here the central atom is xenon, and xenon has already got its octet completed. If you look at the electronic configuration of xenon, right, xenon is an inert element as per the Lewis-Cossel's theory. Xenon would be an inert element. The octet rule says that if any element has 2 or 8 electrons in its valence shell, it would not react and make any kind of chemical bond. But again, formation of molecules like XCF2 or XCF4, where the central atom is xenon, and this xenon is able to make molecules in chemical bonds with fluorine. This is very surprising, and existence of such molecules would also defy the octet rule. This is where octet rule again fails. Fourth point is a very surprising point. This is a very surprising example, that if you consider the elements of group 15 and their hydrides, right? We begin with NH3. The first element is nitrogen. The second element, phosphorus. Third, arsenic, antimony, and fifth is bismuth. So nitrogen, phosphorus, arsenic, antimony, and bismuth. These are the elements of group 15, and ammonia, phosphine, arsine, stibine, or bismuthine. These are the hydrides of group 15 elements. Now, if you draw the Lewis structure of any one of these hydrides, you find that all the atoms have their octets completed. Hydrogens have their duplex completed, and the central atom has its octet completed. They are perfect examples of octet rule, where octet rule is obeyed. However, and so as per the octet rule, all these molecules should be very stable. However, it has been found that the stability of these hydrides moving down the group decreases drastically. In fact, the hydrides at the bottom, right, the hydrides of bismuth or antimony, they are very, very less stable. They cannot be easily obtained. One or two hydrides on the top are stable. In fact, ammonia is the most stable hydrides of this group. The stability decreases drastically as you move down. Again, here you have molecules in which atoms have their octets completed. They are formed perfectly as per the octet rule, and still they don't remain stable. Thus, now what we have is, we have had molecules where octets are not completed, or we have molecules with expanded octets and they all remaining stable, and then at the bottom here you have molecules wherein octets are completed and still some of these molecules not remaining stable. So it is very clear that stability of a molecule cannot be decided only on the basis of octet rule. One of the other problems with octet rule that we need to mention here is that by using the octet rule and drawing the Lewis structures using the octet rule, right, we may not exactly know the shapes of the molecules. For example, water is angular, ammonia is trigonal pyramidal. Now, any knowledge about the shapes cannot be obtained from the Lewis structures given or the octet rule which is used in making those structures. So these are all the failures of octet rules, right? And after doing the limitations of octet rule, we would move on to the types of covalent bonds. How many types of covalent bonds do we have, and what all characteristics they have?